Okay, in this lesson, we're going to learn how to represent certain types of functions as the sum of a power series by modifying geometric series. All right, so quick refresher of what a geometric sequence, series, and the GST is. So remember, we've got our sigma notation. We've got our function or our rule here. So our initial value a, or a sub 1, times r, which is that base of the exponential, to the n power or to the n minus 1 power, depending on what our starting term number is. And any geometric series diverges if the absolute value of that base is at least 1. It converges if it's less than 1, and it converges to this sum. So our sum S equals that initial term, okay, that first term, whatever it is, over 1 minus R. All right, and that's that sum that we're going to be using a lot in this section. All right, so again, quick refresher, example 1. The first term of a geometric series is 2. All right, so that's like saying that's our initial value 1, or first term, and R is 1/3. Write the first 4 terms of the geometric series, the general term of the series, and find its sum. So we want to find those 3 things. First off, let's do the first 4 terms. They give us the first one is 2. So our second one is just going to be multiplying that term by 1/3 every time. All right, so 2 times 1/3 is 2/3, and actually we don't want a sequence, we want a series. So I'm going to put a sum, plus signs in between each one. And again, this is like saying if we were keeping track of our term numbers, this might be term 0, this might be term 1, and then we'll find the next 2. All right, so that next term, we're going to multiply this last term by 1/3. So that's going to be 2 over 3 times 3 is 9, plus 2 over 9 times 3 is 27, and so on. That's our first 4 terms. Check. So then it asks us to find the general term of this series. So then we're looking for, what is that rule? What is that rule? So our initial term is 2, and we're multiplying by 1/3 every time. So that's our base raised to the nth power. All right, since we started at 0, we can just say n is our exponent there. All right, if we want to check that, we can plug these values back into n, make sure we get those 4 terms there. All right, and we will. All right, so we got our general term. So now we want to find its sum. All right, so to find its sum, let's go back to that formula up there. Come back, yeah. All over the place. S equals our first term over 1 minus R. Okay, so S equals our first term over 1 minus R. Let's plug in those values. So 2 is our first term over 1 minus, and our R value is 1/3. All right, 1 minus 1/3 is 2/3. So 2 over 2/3, if we keep change flip, we'll get 3. All right, so our sum is 3. We found our first 4 terms, and we found our rule here, right here. All right, excellent. All right, let's look at example number 2. It says, express the function f of x equals 1 over 1 minus x as the sum of a power series and find the interval of convergence. Include the first 4 non-zero terms and the general term. Okay, so they give us a function here. They don't give us an initial term and a r value like in the last one, and they ask us to write it as the sum of a power series. So what we want to do is we want to compare this to the sum of a power series. So let's kind of copy this down. We've got our first term over 1 minus r, and notice how this function has a similar feel to it as that sum expression does. Okay, so we want to kind of focus and hone in on that. So we can say, all right, so the key parts of this are that we have a 1 down here in the denominator, and we're subtracting some value from it. Okay, we got to have those when we're looking at rewriting functions as the sum of a power series for a geometric series. All right, so with this, we can say, all right, so if that's the case, then my 1 here, that's going to be my first term. Okay, so A1 or first term is 1. So that means that this x here is my r value. Okay, so now we're in kind of a similar spot as in example 1. We've got our first term, we have our r value. So now let's find those first 4 non-zero terms. So we're told our first one is 1. So then our next one we're going to multiply by x. So x times 1 is x. All right, and again, kind of keeping track of our n values. Next one's going to be our term number 2. And then we get term number 3 will give us a total of 4. Again, multiplying by x to get the next one. X times x is x squared. Multiplying by x again will give us x cubed. And so on. And they want us to find the general term. Before we do that, though, well, let's go ahead and do that. So our general term, it just looks like we're doing 1 times x to the nth power. Okay, that's our general rule for that one. Looking at it from a geometric standpoint, our initial value and our r value to the nth power. Again, starting at n equals 0. All right, so again, let's we've answered the question, but let's kind of step back and see what this is saying. Okay, so it says express the function as a sum of a power series. So visually, here's what our function looks like. Okay, so we get f of x equals 1 over 1 minus x. That's what we were given. All right, it's a rational function. We've got kind of 2 pieces separated by a vertical and a horizontal asymptote. What this is saying is that we can represent this function as a series. All right, we can rewrite this function as a series, and based on what the interval of convergence is, which we'll find next, it's going to converge to that function within that interval of convergence. All right, it's going to model that function, essentially represent that function over that interval of convergence. Okay, so let's look at it. Let's kind of look at the series kind of as partial sums, adding one more term at a time. And let's say, all right, so if I name this g of x, then that first term was 1. Okay, so that gives me an approximation at our center 0 of 1. All right, so it's always converges exactly at the center and sometimes more. All right, this one is only the center. So what if we add on the next term? So plus x. Okay, so plus x. So now, if we zoom in a little bit, all right, we can see that's actually the tangent line right there at that point. That gives us a better approximation, especially of the rate of change. All right, let's go to our next term. Our next term was x squared. Okay, so let's add on x squared. And now you can see, wow, that gives a much better, modeling of that function right there around that center. And then we could add on x cubed. Okay, so even better. Add on x to the 4th. Again, better and better and better. And it's looking like we're trailing off at -1 and can't really see in the positive sense. So let's find that interval of convergence, which we take our r value, just like we did in the last section. Take our r value, which for us is x, and it's got to be less than 1, all right, for it to converge. And so x is less than 1, and x is greater than the opposite of that right side 1. Okay, so that means between -1 and 1, this is our interval of convergence. Okay, which makes sense when we look at our graph. Again, if we plugged in more and more of those values, we would see a better model approximation just between -1 and 1. And actually, if we went and we rewrote that function as that sigma, all right, so as that sum, we can't put in infinity here, but if we type this in as some variable a into Desmos and make that a slider, we can make that a value bigger and bigger. All right, so if we just make that a, let me turn that on. That's our purple function there. That's the same thing as just the 1 here. Partial sum, adding up just the first 2 values. That's that, like we just saw. The first 3 values, and so on. All right, then we start to see again, better and better and better approximation. You could go on more and more and more and more. All right. All right, so that's the visual of what we're doing. I don't want you to lose sight in all of this algebra with these geometric series of what we're actually doing with this. We're modeling an actual function with a power series. Okay, example 3. So again, double checking example 2. We've got our first 4 non-zero terms here. We've got our general term here, and we've got our interval of convergence here. Okay, making sure we check all our boxes. All right, example 3 says express the function f of x equals x over 1 plus x squared as the sum of a power series and find the interval of convergence. So again, same thing. Let's start with that rule for finding the sum of a geometric series that converges, and then let us compare it to the function that we're given. All right, so we've got x over 1 plus x squared. Now, this one doesn't fit quite as nicely as that last one. We don't have subtraction there, but all we got to do is rewrite it. All right, addition can always be rewritten as subtraction of the opposite of the second term. Oops. Okay, so now we have that. Let me change, huh? That's cool. Playing this game again. All right, so I guess we're purple from here on out. Now we've got that 1 that we need. We've got that subtraction that we need, so we can pull out our initial value. We can pull out our r value. And we can build our power series from there. All right, so my initial term is x. And I'm going to add on to that my second term, which is going to be x times this. So that's subtraction. So minus x times x squared is x cubed. All right, for keeping track of our n values. Just switch this one out each time. That's cool. All right, x cubed times negative x squared. So we're going to alternate back and forth. We're going to increase our exponent by 2, alternate, increase the exponent by 2, and so on. That's our first 4 terms. That's as much as we need. So now we need to come up with a rule. So you can either say, all right, so my geometric rule, if I'm looking at my initial value and my r value, is just going to be initial value times r value. Whoa. To the n power. Or we can say, if we kind of ignored that and said, well, let's just look at our sequence that we just wrote out and say, all right, so everything's got a base of x. We've got an alternating series, so we're going to have an alternator, so a -1 to the, and then if we put just n to the 0, that's going to work out. To the odd power is going to change the negative. That'll work out. And then we need to look at our exponent. So how can we rewrite our exponent in terms of n? And those are, if we make this 1, these are just our odd numbers. So our odd numbers can always be written as 2n, either plus or minus 1. In this case, we're going to do plus 1. Okay, so just another way to write our rule, our general rule for that power series. All right, so we've got our power series, first 4 terms. We've got our general rule in a couple of different formats. Now we need our interval of convergence. So let's take that r value again, and it's got to be less than 1. All right, so negative x squared. Actually, the absolute value of that is just going to be positive. So x squared less than 1 and x squared greater than negative 1. All right, well, if x squared is less than 1, x squared is always positive. So we know it's got to be, let's see, what can we square to get 1? It's just 1. So we're looking at between negative 1 and 1 for our interval of convergence. All right, looking good for example 3. Let's move on. 4, 5, 6. We got 3 more to go. Example 4 says find a power series representation for f of x equals x cubed over 1 plus 2x. Include the first 4 non-zero terms and the general term. All right, so same directions. They give us a function here. So let's work it out the same way. Switch. All right, we want to use our sum of a converging geometric series as our model, and we're given the function x cubed over 1 plus 2x. Okay, so again, we've got the 1 there. We don't have subtraction. So again, we're going to rewrite it. 1 minus the opposite of that second term, negative 2x. So our first term is that x cubed on top, and our r value is opposite of 2x. All right, so let's use that to build our first 4 non-zero terms. All right, initial one is x cubed. Next one, we're going to multiply by negative 2x. So again, we're going to alternate signs. We're going to have a 2 up front. X cubed times x is x to the 4th. All right, same thing again. Alternate signs. 2 times 2 is 4. X to the 4th times x cubed is x to the 7th. If we're keeping track, wait, let me switch. Nice. We've done 3 terms so far. Let's find the term when n equals 3 and we'll be good. Let's see, that one should have been addition, right? Positive, negative, positive. We should be alternating. 4 times a negative 2 is a negative 8. And it looks like we're adding, did I just mess that whole one up? I did. We're multiplying by negative 2x, not x cubed, Mr. Flory. Let's fix that. All right, so times 2x, I got that. That should be x to the 5th. X to the 6th, and so on. All right, sorry about that. So let's come up with our general rule. So again, if we're using our geometric format, then our initial term, where'd that go, is x cubed. Our r value is negative 2x, so we could write it like this. Or looking at our sequence, it looks like they all have, let's see, we're alternating. So we've got that alternator in there. The first one's positive, so we can do just to the n power. We have, what else do we have? Looking at our coefficient, we've got a coefficient of 2 being multiplied by 2 each time. So we can say, okay, so that's going to be 2 to the n. And then for our variable part, we've got a base of x. And this 3, if we look at that exponent as it relates to our n value, it's always 3 more than our n value. So we can say x to the n plus 3. All right, so 2 different ways to model the general rule of this power series. All right, what else do we need to do? First 4 non-zero terms and the general term, and they don't ask for the interval of convergence for these 2. All right, let's look at example 5. All right, find a power series representation for f of x equals 1 over 2 plus x. Include the first 4 non-zero terms and the general term. All right, same direction. So sum, initial value over 1 minus r. Let's compare that to our given function, which is 1 over 2 plus x. All right, so we said we needed to have, if we look up at that last example, we need to have the 1 the same in the denominator, and we got to have that subtraction there. So far, that 1 has always been there. We just had to kind of fiddle around and modify so we can get that subtraction there. In this one, though, we don't have a 1 in that denominator. So we have to manipulate it until we get 1. So we can either think about it as dividing by 2 or multiplying by 1/2, but we're going to do that on the top and the bottom. Excuse me. So I like to think about it as multiplying by 1/2. All right, top and the bottom, so that we don't change the value. So that leaves us with 1/2 in the top. Distributing that 1/2, half of 2 is 1, and plus x, that's going to be plus x over 2. All right, we got the 1 there. All right, well, we don't have the subtraction, so now let's just rewrite that. We still keep that 1/2 in the top. We're going to be okay with complex fractions at this stage, and let's rewrite it just like we did in the last couple terms as minus a negative. Okay, so now we can pick out our initial value and our r value. And come up with our sequence from there. All right, so first term is 1/2. And again, we've got a negative, so we're going to be alternating again. Let's keep track of our n values. All right, we're multiplying by negative x over 2. So our next term is going to be subtracting x over 2 times 2 is 4. Change sign, times negative x over 2. X times x is x squared. 4 times 2 is 8. Times negative x is going to be x cubed. 8 times 2 is 16, and so on. All right, first 4 terms of our sequence. Let's come up with our general rule. Again, initial value 1/2. Our r value, opposite of x over 2 to the n value. Okay, or if we're looking at it as pulling the rule from our sequence, if we kind of break it up into numerators and denominators, we've got that alternating part. So we're going to have an alternator in there. The first one's positive again, so just to the n power. And then we've got powers of x. So we can say x to the n. Those exponents line up with our n values, so that works out. And in the denominators, we've got powers of 2. So 2 to the n, 2 to the 0 is 1. That doesn't work out. 2 is 2 to the first power, so if we do plus 1 there, does that work out? 2 to the 1 plus 1, 2 is 4. 2 to the 3 is 8. 2 to the 4 is, all right, so that looks good. Okay, so a different way to write our rule, not in geometric series form. All right, we've got our first 4 terms. We have our general term. We are good to go. All right, example 6 says sometimes we cannot center a function at x equals 0. In this case, we can try to rewrite the function with a new center showing. Okay, so example 6, last one, says find a power series representation for f of x equals 1 over x. Include the first 4 terms and the general term. So if we start this off the same way, then we've got a problem because we don't have the 1, we don't have the subtraction in the denominator at all. So we've got to get a little bit creative here, and here's the strategy that we're going to use. Okay, so we're going to keep the top like it is for now, and we're going to say, okay, so I want subtraction in there, so I'm going to put subtraction in there. All right, I'm going to put in a zero term or a zero pair. I'm going to put in 1 minus 1. All right, and I'm going to add that to x. Right, because 1 minus 1 is just 0. So we're not actually changing the value of our fraction, we're just changing the form. Okay, what that does is that gives us our 1 here, and that gives us our subtraction. All right, so let's rewrite that one more time. So we've got our 1, we've got our subtraction, but we just want a single term. We just want a single r value after that. So whatever's left, we got to group into a single term. So we're going to need to group this and factor out that negative 1 to get 1 minus x. All right, so now we have our initial value, and we have all of this being our r value. All right, just double checking. We've got our 1, we've got our subtraction. Good to go. Let's keep going. All right, so they ask us to find the first 4 terms and a general term, general rule, just like in the previous problems. So first term is 1. And our rule is we're multiplying by our r value. So we're multiplying by 1 minus x to get our next term. Okay, so 1 minus, and again, this is positive, so we don't have to alternate signs on this one. 1 times 1 minus x is just 1 minus x. Okay, our next one is going to be this term, 1 minus x times 1 minus x again. So to save some space and to write it as succinctly as we can, let's use exponents. So 1 minus x times itself is 1 minus x squared, and we're just adding factors of 1 minus x, so that exponent just increases by 1 each time. All right, so that's our first 4 terms. As a general rule, geometrically we can write it as 1 times x minus 1 to the nth value, and that would be the same as if we were to just look at it. We could drop the 1 if we wanted to. Either way, that's what happens on our nth term, or our general rule. Okay, so that is taking a given function and using what we know about geometric series and the sum of converging geometric series to rewrite or to model a function using the sum of a power series.